Hi, I'm Jamie with Chegg Tutors. Today I want to talk to you about angular momentum, a really useful concept in physics or mechanical engineering when you're dealing with rotating bodies, whether in one dimension or three dimensions. Angular momentum is the same kind of idea as linear momentum that we're more familiar with, P equals mv, but for a spinning body. So the equation looks a little different. If L is angular momentum here, then we have L here. We have it's a vector. It's a cross product between I, the moment of inertia, which is the equivalent of mass for a rotating body, and W, or omega, the angular velocity. So we have a mass-like term and a velocity-like term, but applied to rotating bodies. Now, in general, angular momentum is a very complex thing. This is what we can use to understand the motion of gyroscopes. The conservation of angular momentum is why gyroscopes act the way they do. But at a very simple level, we can also use it to understand one-dimensional motion, clockwise or counterclockwise of a CD or of someone who's skating in a very simple way. So in the one-dimensional case, we have a scalar. It could be positive or negative depending on the direction of the velocity, but it's just going to be a scalar, the equivalent of mass, the moment of inertia, times the angular velocity. That's the case I want to deal with right now, and then we'll generalize. Now, like I said, angular momentum has a conservation law just like linear momentum. As long as we're in an inertial frame of reference and there's no acceleration, then angular momentum is conserved. L is I times the cross product with W. This vector L is always going to have both the same magnitude and the same direction as long as there is no force being applied, or torque, rotational force, being applied to the system. Let's apply this to understanding two different rotating bodies. This first one is a disk. It's a solid disk, and it has a mass m. The second one also has a mass m, but it's a much bigger disk, so it's less dense. It has a greater volume, greater surface area, but the same mass. Let's assume also that omega, or the rotational velocity, is the same for each of these. And let's think about which one has more angular momentum. Now, if this was just linear momentum and these were moving in a straight line, mass is the same, angular velocity is the same, so we'd have the same linear momentum. But it's a little different when we're considering angular momentum, because you see, the moment of inertia doesn't just depend on how much the mass is, but also where the mass is spread out. The mass is spread out over a smaller area in this one. It's spread out over a much larger area in the second disk here. In this case, the moment of inertia I is proportional to the radius squared. So if this guy has a radius of r and this guy has a radius of 2r, L2, the angular momentum of the second disk, is going to be 4 times L1, despite the fact that the disks have the same mass and the same angular velocity. So even though there's an analogy between linear momentum and angular momentum, we do not want to consider them the same thing. They actually behave quite differently in a lot of ways. I wanted to apply this conservation of angular momentum to why skaters, when they're trying to have a faster spin, pull in their arms. So in this case, again, this comes down to moment of inertia. Let's consider this is the skater at time 1 when he or she has his or her arms quite wide and is going to jump up and pull in for a spin at time 2. Now, because the mass is farther away from this person's center of mass when he or she has their arms out, the moment of inertia for the skater in this position is greater than the moment of inertia for the skater in this position. Again, there's no extra force being applied to this person from outside, so we have conservation of angular momentum. The moment of inertia at time 1 times the speed, the angular speed at time 1, is equal to moment of inertia times angular speed at time 2. Now, if I1 is greater than I2, this means that W2 or omega 2, the angular speed at time 2, is going to be greater. This is exactly why skaters get a faster speed on a jump when they pull their arms in, and why they're going to do that in a figure skating or a competition. There are generalizations of this to 3 dimensions, like we said with the gyroscope. This involves taking a tensor or the cross product of vectors, and is a lot more complicated. You're going to need that for things like spaceship design or calculating the orbit of something, or even considering a rotating rigid body in 3 dimensions. That gets a lot more complicated. But I want to give you the simple version so we can think about the concepts of angular momentum before we get too involved in the calculations. If you do want to get into the calculations, check out some other videos on Chegg. But for now, that's all. And see you next time.